circular rates. So we're talking about circular motion, but we are also talking about angular motion in a way. We'll get more into angular motion later when we talk not just about an object that's orbiting like you see here, but an object that's spinning. And if you look really carefully, you can see that this object is both orbiting and spinning. But right now, we're not as worried about all the dynamics of what's happening. We're just really interested in trying to convert between different types of quantities as we make sense of circular rates. So here's an example. Let's say Turgeon's spinning rubber stopper. The string is 0.7 meters long. Let's find the frequency, angular speed, linear speed. First thing, you need some information. Let's say we time it. All right, there wasn't enough information. You would be given this in a problem. I should have said that. So the time is 5 seconds and we count 10 revolutions. Okay, fine. So right away you look at that and you say, well, I know that it's going to take half a second for each revolution. And I know that it's going to take, it's going to make 2 revolutions every second. So now it's a question of vocab and terminology. It takes 0.5 seconds for 1 revolution, so we call that the period. Period is a time. It's a time period. You should write that down. It's a time period for 1 revolution. 0.5 seconds, that was easy. I just took the time and divided by the number of revolutions. The frequency is 2 revolutions per second. If you think about frequency just as the number of cycles, revolutions, events per second. And speed is, well, let me go back to frequency for a sec. So let's look at some equations. So I can use this one. We have this pair of equations that involves frequency and period. And my period equation is that the period, you'll notice, is 1 divided by the frequency. And thus, you'll notice that the frequency is 1 divided by the period. So these two kind of go hand in hand. Frequency and period are inverses of each other. That's a good way to say it. And it's also worth saying that the units of frequency are the hertz. And what is a hertz? A hertz is a per second. Okay? Just like Avogadro's number was a per mole, 1 hertz is equal to, see, this is a hertz, and it's equal to a 1 over second, and it's seconds to the -1. Those are just different ways of expressing that. Now, linear speed is just distance over time, but since we're talking about a circle, distance over time, linear speed, also known as the speed, what we're saying is literally, if you go back and look at this, as we trace this object moving around this circle, we're saying it's just literally how fast, if I just travel, how fast is this thing moving, like if it were a car, and what would its speedometer say? Linearly, that speed is distance over time, so it's 2 pi r over the time period. And that time period is a capital T. I should have emphasized that. So look, this capital T is telling me not just any arbitrary time, but specifically the period. This is a lowercase f for frequency. This is a capital T for period. So the distance over time, I'm going to plug into this equation very quickly. You can do this along with me. 2 pi times 0.7 all over the period of 0.5, which you can see just basically ends up being 4 pi times 0.7. I'm plugging that in my calculator. 8.8 meters per second. Notice the units are meters per second because we're getting a linear speed. Okay, so these are my answers so far. And now let's get the angular speed. So first of all, angular speed. Angular speed is in radians per second. Well, that begs the question, what's a radian? Okay? A radian is a way of measuring angular displacement, the extent to which something rotated. So 1 radian is, sorry, I'm going to say this another way. 1 revolution is 2 pi radians. There are 2 pi radians in a circle, in a circular revolution. So I'm going to write down, I like to go from frequency, so if my frequency is 2 hertz, I'm going to write down 2 revolutions. This could also be cycles. Okay, it could be oscillations. 2 revolutions per 1 second. Notice how I'm writing that? Now I'm going to extend this line. I'm going to do the chemistry dimensional analysis kind of thing. And I know that 1 revolution is 2 pi radians. This seems to make everything work because you can see that I'm going to cancel out revolutions and I'm going to multiply across and get my answer now. And this is just going to be equal to 4 pi radians per second. I don't know, 12 point something. Radians per second. And here's the weird part. There's a new variable, and that variable is a lowercase omega. It's kind of like a curly W. It's not W like this. It's like a curly W. And my angular velocity, or angular speed, is 12.57 radians per second.